Okay. So yeah, this night. So we start with an introduction to waves. There are two types of waves. There are transversal and longitudinal waves. So can anyone tell me what is the difference between both? What is the difference between a transversal and longitudinal wave? I know someone typing something in the chat, but you need to say something. What is the difference between a transversal and longitudinal waves? Okay, so transversal waves, that's where you do have the particles go up and down, perpendicular to the speed of the wave, while for the longitudinal, you have the particles go back and forth, parallel to the speed of the wave. So that being said, for a string, the wave speed is inside each medium is like this. The speed of a wave is a property of a medium. So each medium has a specific speed for the wave. And for a string, the speed the wave speed inside a string is the square root of the tension of the string over mu, where mu is being the linear density. So it is actually the mass over the length. This is flipped. And Ts is being tension. Okay, so with that in mind, let us try to solve this. So which of the following actions would make a pulse travel faster along a stretched string? More than one answer might be correct. If so, give all the correct. Move your hands up and down more quickly as you generate the pulse. So as we move your hand up and down more quickly, what would that do to the wave? So moving your hands up and down more quickly. What would that change? Would that change anything in the wave in the first place? Okay, let's do this. If you think it will make it faster, raise your hand. And if you don't think so, don't raise your hand. Okay, is moving your hand up and down more quickly will make the wave go faster? If yes, raise your hand. So the only one is Victoria. Actually, no, because moving your hands up and down more quickly, that just simply increases the frequency. So if I open my camera, so moving your hand up and down more quickly as you generate the pulse, that only increases the frequency. And as you see, I don't know what that is. For these speeds, it does not have to do anything to do with the frequency. It's just the tension and the linear density. Okay, so move your hands up and down larger distance. So if I move my hands up and down more, would that change the speed? If no, raise your hand. So I do have the wave and I raise my hand up and down for the distance. Would that change the speed? If no, raise your hand. If yes, don't raise your hand. So I'm taking everyone is saying yes, it will change the speed, which is not the case, as moving your hand up and down, it just increases the amplitude. And the amplitude is, again, has nothing to do with the speed. Now, use a heavier string of the same length under the same, for the same length under the same tension. Would that increase the wave speed? Yes or no? Need someone to say something. No. Yes, it's okay. So you using a heavier string, that means your mu, your linear density, increases. And looking here at this equation, if the mu increases, that means your overall speed will decrease. So I said, will it increase? And you said no. So I will take that. Yes, this will not increase the speed. So what about if you use a lighter string? Would that increase the speed? Yes or no? Yes. Okay. So you stretch the string tighter to increase the tension. Would that increase the speed? Yes or no? Yes. What about you loosen the string to decrease the tension? Would that increase the speed? Yes and no. Well, I assume people know no. But now the real question is, if you put more force into the wave, so if you put more force as you generate the wave, will that make it go faster? Yes or no? Yes, indeed. It will increase the speed as when you put more force, it will increase the tension in the string, and that will lead to the speed to be faster. Okay. So now, when we move to one-dimensional, the main thing about that section is just knowing what is a snapshot graph and what is a history graph, and how to get one from the other. So for a snapshot is basically you plot the amplitude with respect to the distance. So if you snapshot means like when at an instant of time, just freeze the wave. At some point, it will look something like this. But then at the next instant, it would change. Like after a little bit of time, the wave will have moved. So its position changes. The shape is the same, but its position changes, and so on. But as you can see, that the particle is at the same place. It doesn't go right or left. It just goes up and down with the wave. So for waves, there's a difference. The particle does not change its position. It just goes up and down, doesn't go right or left, just up and down. That is for transversal wave. For longitudinal, the particle can go right and left. But that's it. But it doesn't change from that line. It just keeps oscillating back and forth. It doesn't keep going right or keep going left. It just stays where it is and just oscillate back and forth. So for a histograph is you plot the same amplitude, but now against time. So for a specific point, at a specific point, you know, like how the wave moves over time. So let's say we took this point as a reference point, and we want to see how over time the wave will look like. So let's look at this, at the following. Let's say that this is a graph for t equal to 0, and the speed is equal to 2 meters per second. Okay. Yeah. So yeah, we look at 2 meters per second, and this is our reference point. This we want to see how over time at the point 6 how the wave will look like. So what would happen is we have the leading point is at the 4 mark, and since the speed is 2 meters per second, so after 2 seconds, after 1 second, after 1 second, it would have moved till 6. So it takes 1 second to move from here to there. So actually this should be 1. So we know after 1 second it will reach at 6. That's why this point is over here. And I say the second point has a distance of 2 meters between them. So how long would it take for this point to reach 6? It would take 1 second, 2 seconds. So that's why we have this point will be at the distance at the 6th mark after 2 seconds. And if we have this at a distance of 6 meters, then it will take 3 seconds to reach the point 6, the 6th mark. So over here, it will take 3 seconds. So as you can see, the difference between those two graphs is just the mirror. So if you put a mirror halfway in there, it would just the history will be the mirror image of the snapshot. So yeah, this is how to get from a snapshot to a history graph. Just take the mirror image of that. So now let's look at this. The graph at the right is the history graph at x equal to 4 meters of a wave traveling to the right at a speed of 2 meters per second, which is the history graph of this wave at x equal to 0 meters. So we do know that the wave moves to the right. So over time, it should move to the right. So if at x equal 0, that means it was previous to this snapshot. It was like at the time before that. So when we have this point being at 4 seconds, that means that's the after fact. We want to see before like the time before that, which is at x equal to 0. So since we have the speed is 2 meters per second, and we want to see it at x equals 0, that means, and the distance between x 0 and 4 is 4 meters, so it takes 2 seconds to reach this point over here. It takes 2 seconds to reach this point over here. That means 2 seconds before, this whole graph was at the left. So this point should be would go 2 seconds before. So if this shifts by 2 seconds, the whole thing will shift by 2 seconds. If this is at 6, will be later at 4. If this is at 8, will be later at 6. So this would be the answer. Then we move on to the next section for sinusoidal waves. Like out of this section, the most important thing that you need to know is this equation. For a medium, any wave have a specific speed, and this speed is v. And for that, V, we know V is going to equal to lambda multiplied by the frequency. And why does that make sense as the following? We know that V is equal to some distance over time. Where lambda is the wavelength, and the wavelength is the distance between two consecutive points, or it's the distance once the wave it's the distance for a full wave for one cycle. So the units of lambda are meters, and for a wave, okay, so let's say like this is a wave. From this point to this point, this distance is lambda. But also between those 2 points, like the wave has a period to go a full cycle, and that period is t, where the frequency is equal to 1 over the t. So basically then the wave speed, it just would be delta over time, where delta over time is delta multiplied by f. That's how we get this equation. And this equation is really important. So if you increase the frequency, the wavelength decreases. If you increase the wavelength, the frequency decreases. Because V is always constant. V does not change. You change those two. V only changes once you change your medium. So if you go from one medium to another, that's when your V changes. So V is a property of the medium, but frequency is a property of the source. So let's say you have a string and you're moving it. So your hand is the source and the string is the medium. So what defines the speed what defines the speed of the wave is the string itself. But what defines the frequency is my hand. How fast or how slow do I move the string? So there's two types of speeds in a wave. Yeah. The first one is being the speed of the actual wave. There's two speeds. There's the speed of the actual wave as it's moving, and there's the speed of the individual particles along the wave. And those are two different things. So over here, this shows for a wave has an overall speed or velocity to the right. That does not indicate the speed of the individual particles over time. So along the wave, each particle has its own speed. And you can see, so like let's say this is our crust, and the speed is moves to the right. That means that this crust will be after 1 second, let's say, will be over here. So that means that this wave goes up, and that this particle needs to go up, and the other particle needs to go down. So that's why over time you see that the particles along the line has increasing velocity upwards. But at the top, you already reached the top. That's the max. You're not going up anywhere. So you don't have any speed over there. So for the crust or the trough, you have the they are the turning points. That's why the velocity is 0. Okay, and there's something we call k, and k is being the wave number. Wave number is just simply 2 pi over lambda, and that helps a lot when we write the equation of the amplitude over time, or the displacement over time. So let's look at this. What is the frequency of this traveling wave? So if we have that the frequency that the speed is 50 meters per second, how can we find the frequency? So we do have v is equal to negative 50 meters per second. How to find the frequency? Does anyone have any idea what to do? Frequency is equal 10 or 10f. Okay. Okay. So you're saying 10. How, I'm assuming that you got the 10 by the wavelength, since the speed is equal to lambda f, and you got the lambda by the following. You know, at this point, the distance between them is lambda. That's a full wave. That's why this is lambda. So we have your lambda is equal to 10 meters. So that means that, yes, as you said, you have 50 is equal to 10 multiplied by f. So f is, yes, indeed, is equal to 5. So this would be the answer. Okay, so now we jump to sound and light waves. So sound waves are longitudinal or transversal. What do you think? For sound waves, what are they? Are they longitudinal or are they transversal? Sounds writing something. When you say sound waves, how does sound wave propagate through air? Is it longitudinal? Is air get compressed? Or does the particles go up and down to get your ears? Longitudinal, yes, yes indeed. So it's not transversal. It is longitudinal, yes, because as you speak, you compress the air and so on. And the speed of sound in air is 343 meters per second, which is pretty fast. Then, okay, now we jump to light waves. Are light waves longitudinal or are they transversal? Yes, indeed. Light is transversal. Light goes up and down. Okay, and the speed of light in vacuum is this insane number, which is the fastest thing in the universe. Anything goes faster than that burns, literally. And you can just approximate that to 3. Like this most of the time would work, unless they specify it, like, yeah, be accurate, and you just take the first 3 numbers and put the rest as 0. Well, yeah, you can find the frequency or the wavelength of light or sound using this same equation. So if you know that you're in the question, your medium is air, so you know this is the speed of sound in air, and it gives you some frequency and ask, oh, what is the wavelength? Just simply use this. Same thing for light. If you know, like you're in vacuum, so you know this is the speed of light, and it gives you some wavelength. And it's like, oh, what is the frequency of light? Just exact same thing. Use the same equation. Okay. So now we'll look at when we get from one medium to another. So when wave passes through different materials, their properties changes from the speed and the wavelength, but the frequency stays the same. Okay, so as you're going from one medium to another, like let's say you're going like you even as a person, like you're moving, and you're going from pavement to sand. The sand is much harder, is a different medium than pavement. And sand, you can look at it as like it's harder to walk at compared to the pavement. So your speed as you're walking would decrease. Same thing. If you have a wave and it gets from one medium to another, it gets the speed changes. So if you're getting from one medium to a more dense medium, your speed decreases. It's like the speed of the wave decreases. And says since the frequency is a property of the source, it is independent of the medium, so the frequency stays the same. Then we have, like again using the same equation, v is equal to lambda and f. Since f is the same, it's not changing. When you have your speed changes, that means that your wavelength will also change. So and that here comes something called the index of refraction, which is n, and n is equal to the ratio between the speeds. Like if it was this c is for light when it's vacuum, or it is for sound when it's air. And the second v is the speed of the wave inside the new material. So they can normally give you like, oh, tell you like, oh, we have the n is equal to 2. What is the new v for air for sound? What would that be equal to? So you know, okay, that's easy. 2 is equal to the speed of sound in air, which is 343. And we're trying to find what is the new speed of sound. So that means that v is equal to 343 divided by 2. That would be the new speed, and so on. You can do so many things with this. So for our question, light wave travels from left to right through 3 transparent materials of equal thickness. Rank in order from largest to the smallest the entities reflection in A and B and C. So let's say this is vacuum. So it has a normal wavelength. Then it gets to something denser because vacuum there's no density there. And then you get to some material, so it's more dense than vacuum. So the wavelength, decreases. So here, this is the wavelength. Then going from NA to NB, you see that the wavelength increases. Does that mean it's more dense or less dense? If you go from one medium to another and you find that the wavelength increases. So let's look at this equation here. Since the frequency is the same, once you have your wavelength increases, that means also the speed of the wave increases. Right? So if the speed of the wave increases, that means that the new material is less dense than the one before it. So if it's less dense, that means the n is smaller, because the smallest n is equal to 1. So, and n can get really like much bigger than 1. So the smaller your n is, the less dense your medium is. So now we know that NB is less than an NA. What about NC? Is it less or more than NA? So you have your frequency, you have your wavelength decreases. If your wavelength decreases, NC is less than NB. Yes, indeed. Yes, indeed. So NC is the less dense, then NA. Okay, there's something wrong here. Okay. Okay, so we've established that NB is less than NA. Since the frequency is smaller than NB and NA, so that means NC is even bigger. Okay, you have NC is inversely proportional to the V. And you have V is inversely proportional to lambda. That means that N is inversely proportional to your lambda. So if your lambda increases, your N decreases. So then, since this is the bigger lambda, this is the smallest N. This is the smallest lambda. This will be the bigger N. Okay, so for waves in 2 and 3D, 3 dimensions, there isn't really much to do. They're all roughly the same thing. Like if you know just the normal properties of waves, there isn't really much difference. Like if you know how to deal with a wave in 1D, it's the same thing how to deal with it in 2 and 3D. They're pretty much the same. There isn't really much of a difference. But the only part in this section that's different is the phase difference and how to know it. So a phase difference is if you have okay. So usually we have the equation for a wave as like some amplitude sine of some constant multiplied by t. Okay, plus a phase constant. This is the phase constant. So usually when this is 0, we would have our wave look like this. More or less. But what if the wave wasn't perfectly like that? What if it looked something like this? So it's not perfectly aligned with this point. There's a little bit of change. And that change, that's what's called a phase change. And that's why you need the phase constant in there. So in general, for a full wave, the between, like for a full wave, the phase difference is 2 pi. So if I open Desmos and I show you this. So yeah, this is like a normal wave. This is our A being the amplitude and C is being just like the frequency of the wave. So if I increase the amplitude increases, making it negative, it just switches more or less. This is the frequency. So if I get higher frequency, the wavelength gets closer. If I have lower frequency, it just gets bigger and bigger and bigger over time. So now, what if our wave was a little bit shifted? And that's where it comes. Oh, need to make plus B here. Yeah. And here comes, this is being our phase constant. So that accounts for that shift. So if you have it at 0, just gonna be our normal our normal wave, if it changes, it makes it like if it's not zero, then the wave changes, shifts to the right or to the left. A nice thing is that that a wave repeats itself each 2 pi. So every 2 pi, it repeats itself. So if here I have 2 pi, it just looks exactly the same. It did not change. So that means if I only looked at 1 pi, that means it'll be halfway through. So our wave was in the beginning over here. This is how it started. But now when I change it to 1 pi, it goes halfway through the wave, and so on. So if you want to go a quarter of the wave, make pi divided by 2. If you want to go 1/8 of the wave, make it pi over 4, and so on. So this is being the wave phase constant. Okay. So what is the phase difference when asked what's the phase difference between a crust and a trough, at the adjacent trough? Okay. So if I made this 0, yeah, this is being a crust, and this is being a trough. This is a crust, and this is a trough. The distance between them, what is the phase? Is it a full wave? Is it a half a wave? A quarter of a wave? How much of a wave is it between one crust and the next trough? So between a crust and a trough, how much of a wave is it? Is it a full wave, or is it just half a wave, or a quarter of a wave, or I don't know, 5/6 of a wave? Yes, indeed. Yeah, it's a pi because it's half a wave and half a wave. Since a wave repeats itself each 2 pi, so the difference would be a pi. And you can literally see it over here. You have pi over 2, you have 3 pi over 2. So this is half a pi and this is 1.5 a pi. So the difference is a pi. Yes, indeed. So that would be the answer. I just said we'll do question 29 just to show you an example for a wave in 2 and 3 dimensions. So a circular wave travels outward from the origin at one instant of time. The phase at r equal 20 centimeters is 0 radians. And the phase at 80 centimeters is 3 pi. So what is the wavelength? So basically, if we drew this, say this is being the source, and roughly know at 20 the phase is equal to 0. I believe so. Centimeters, yes. And then at 80, it's being it's another 60. So here the phase is equal to 3 pi. So between this wave, or this point, and this point is how many waves? How many waves are between those 2 points? Is it just half a wave between them? Is it 2 full waves between them? Is it 1 wave? How can we find that? You can find that using the phase. Like, a full wave repeats itself after 2 pi. So if you have the difference between them is 3 pi, so how many waves are between those 2 points? Yes, indeed. It would be 1.5 waves. So for 60 centimeters, it corresponds to 1.5 waves. So if you want to find what is the wavelength for one wave, just simply do that. That means that lambda is equal to 60 centimeters divided by 1.5. That will equal to, it's like 25. It's 40. Oh, that was too far off. Well, yeah. So your lambda is equal to 40 centimeters. And that's your wavelength. That's just simply what it would be, more or less. Okay, keep going. So what is a power, what is intensity, and what is decibels? So power is just energy per second, and it has the units of watt. And the intensity of a power, the intensity is the power divided by the area. So just P over A. Where yeah, P is the power of the source, and A is whatever the surface you're looking at. So if you're looking at the circle, the area of a circle is not 2 pi r, it's pi r squared. So the intensity for a full circle would be P over pi r squared. And if you look at a sphere, the area of a sphere, that means you're looking at the surface area of the sphere, and the surface area of a sphere is 4 pi r squared. So that's the surface area of a sphere. So then the intensity of a sphere is the power divided by 4 pi r squared. The ratio of the intensities between 2 points in a sphere can be given by that. So as you can see here, that for a sphere, the intensity is inversely proportional with r squared. So the further you go away, so if you doubled your r, you'll have 1 over 4 for the new I, and that's basically what it says here. So let's say that this is your source. This is R1. This is your R2. So if you have here I1 and I2, the ratio between the I1 and I2 is the ratio between R2 squared over R1 squared. And also, since the intensity is equal to P, and P is equal to E over seconds, with being the energy, and the energy of a wave, if you remember, it's half K A squared. I'm just divide that by seconds. So more or less, you do see that where A being the amplitude. So you see that I is proportional to A squared. So if you double the amplitude, you quadruple the intensity. Okay, so now we look at decibels. So decibels is just some measurements to say how intense is the sound. So we can find that using we denote it by beta. This would be, and it's equal to 10 multiplied by the log of the ratio between two i's. This I naught is basically what is the minimum intensity a human can hear. So you take like if anything with this intensity, you can't really hear it. You like next you can't hear it. So this will take this as our reference point, and we compare any other intensity to that point. So let's say if you have something that has an intensity of I naught, like so if we put here, if we put the, here I naught, that means that we will have I naught over I naught, which will take all this log to 0. So then your sound intensity is 0. But when sound intensity is 0, that does not mean there's no sound. No, there is sound, but you as a human, you can't hear it. But other animals can hear it. And for humans, the pain threshold is 130 decibels. And since the intensity level beta is multiplied by log of base 10. So if you want to double beta, that means you need to make I multiply by 10. You need 10 of I, just double the intensity level, the decibels. So let's look at this. For four trumpet players are playing the same notes. If 3 of them suddenly stop, the sound intensity decreases by. So let's say in the beginning we had 4 people, so let's say the intensity was 4x. And now once 3 of them stopped, so the new intensity is just 1x, because there's only one trumpet still playing. So how can we find by how much the intensity level decreased? Okay, we do have our beta is equal to 10 multiplied by the log base 10 of some i's. Call this is in general. This is not for this question. This is what is beta in general. So how can we use this to find by how much the intensity decreased? Does anyone know? Okay, if you don't, we can look at it this way. If we took our reference being our I1, so that means the change in beta will equal to 10 log of base 10 of I2 over I1. You take the ratio between both of them. And this ratio is equal to 10 log of 1 over 4. And if you saw that, that would be negative 6.00 something. So since you have negative change, that means, and here it asks you decrease, so that means this is the answer. Okay, then we move to Doppler effect. Okay, so Doppler effect is basically when you hear anything moving next to you, you feel that its sound changes over time. So you hear it so high, and then as it passes you, it doesn't sound as high, it sounds low. And by high, I mean by sharp. It sounds like really sharp to you the closer it gets. And the further it goes, it doesn't sound as sharp. sounds softer. So that is because of something called the Doppler effect. So as a source of sound is moving next to you, the frequency you hear changes. And the frequency, how the frequency will change, that would depend on who is moving. Is you're standing still and the source is moving towards you, or the source is standing still and you're moving towards the source. So if the source is moving, like you're standing still and the source is moving towards you, as it's moving towards you, the frequency will be higher. And you can see this by this video over here. So as it goes, the wavelengths, the waves in the front gets closer together, and that means that their wavelength decreases. And since the speed of the wave is constant, so if the wavelength decreases, that means the frequency will have to increase. So if you're standing here and the source is going towards you, you see a higher frequency. But if you're standing behind it, you receive a lower frequency. And you can calculate both of them using these equations, where F naught is the frequency of the source in the beginning, and Vs is the speed of the source. This V is your speed. Is the speed of the wave in general. And if you want to find the lower frequency, as if you're behind it, just change the sign. Instead of minus, that will be plus. Those equations are if the source is moving towards you or away from you, either. But now, if you are moving towards the source, the equation changes. So this is the new equation, where the V naught is your speeds relative to the source, and V just the normal wave speed and the frequency. And this is the frequency of the what? This is the frequency of the wave normally, of the source. Okay, so have Amy and Zach are listening. Both are listening to the source of sound waves that is moving to the right. Compare the frequency each hears. So for Amy, does the frequency, is it lower or higher if both of them were stationary? Like, to Amy, the source is relatively stationary. Does that mean it will be the same frequency, or the frequency will be more or less to Amy than normal? So as both of them are moving, with the frequency to Amy, would it be less or more than the normal? Would it be the same? I know that's... No, it would not be the same, because it would not be the same because why? Because those two equations are a bit different. Well, first, the change as the source is moving, the change it does to the frequency is much higher compared to if you're moving towards or away from the source. So in this case, even though both of them relative to each other, they're standing still, but actually the source is getting further away from its waves. So the wavelength itself is bigger. So that means the frequency received by Amy is less. So if, let's say, this is f of Amy will be actually less than f of source. What about Zach? Zach is going towards this source, and the source going towards Zach. Would the frequency be higher or lower compared to the source? Be higher, yes, indeed. So then we have like that f of z. So that means overall this would be the answer. Okay. Somehow I hoped we would have finished this 20 minutes ago. Okay, so let's do just the following questions. Let's do 45. Let's start with that, yeah. Okay. Okay, so let's see. The following figure is a histograph at 0 meters of a wave traveling in the positive x direction 4 meters per second. What is the wavelength? So we have speed. I'm sorry, it asks, yeah, what is the wavelength? We have speed is equal to 40 centimeters per second, and we're being asked, what is the wavelength? What to do? What do I need to find first? That doesn't help. This thing is really stupid. Yeah, you need to find f. Yes, indeed. So v is equal to lambda multiplied by f. So that means that lambda is equal to b over f. So we need to find what is f. And lucky enough, we overdid it. So it was 45. Yes, it was 45. So this is our history graph. So can you find what is the frequency from this? Okay, this is time. So how long does it take the wave to complete a full cycle? That's your question. That would be your period, and from your period you find your frequency. I didn't even need the frequency. You can just do VT, because one over frequency is time. So 0.2, yes indeed. So then you would have 40 centimeters per second multiplied by 0.2 seconds, which is equal to 8 centimeters. So this is your wavelength. Okay. So the second question is, what is the phase constant? So to find a phase constant, do we need it over time or do we need it over distance? Or it doesn't matter? Where is the phase constant we found? Yeah, or it doesn't matter. Okay, yeah. So in here, what is the phase constant? where should the wave start? The wave should start from here. So it's a little bit ahead by this amount. 3 over 2 pi. 1.5 pi. You can say that. You can say 3.2 pi, or you can say a negative half a pi. So either are totally correct. There's no like this is right and this is right. So if you said okay, this is the start of my wave. So this is half a wave, and this is, I'm sorry, this is if this should be the start of my wave, you're gonna say this is a full wave and a quarter. Actually, no, it should be over 4, not over 2. Because yeah, this is a quarter. I'm sorry, this is a quarter of pi over 4. So you can say, if you looked here, if we made this pi over 4, I'm sorry, yes, you're right, it's pi over 2. Yeah, so it's either pi over 2, negative pi over 2. This is the same as we have here. So yeah, it's either pi over 2 or 3 pi over 2, as you said. Both of them are correct. But yeah. For the what is when it asks write down the displacement equation of this wave. I think that's gonna come in the exam because they said skip 16.6, and both of them are discussing the displacement wave. That's why I did not cover it. But yeah. Then the next question is 61. Let's look at 61. Okay, so a string that is under 50 newtons of tension with a linear density of 5 grams per meter. A sinusoidal wave with an amplitude of 3 centimeters and a wavelength of 2 meters travels along the string. What is the maximum speed of a particle? No, we can't do that. This is I really doubt it because this is going to be also the equation of displacement. So I don't think that will be there. So let me pick another question. Let's take this one. Yeah, this is acceleration. Nope, still no. It's quite hard not to find one that uses the displacement equation because I really doubt it's gonna come. Maybe it would. I really don't know, but I quite doubt it. Okay, let's do this for now. 67, I'm sorry. So LASIK eye surgery uses pulses of laser light to shave off the tissue of the cornea, reshaping it. A typical LASIK laser emits 1 millimeter diameter laser beam with a wavelength of 193 nanometers. Each laser pulse lasts for 50 nanoseconds and contains 1 millijoule of light energy. What is the power of the laser? So here you have your energy, here you have your time. Okay, so the givens. Have the energy is equal to 1 millijoule. You have the time is equal to, it's not the period, it's the time of how long it lasts. That's different. So just let me call it with small t. It's 15 nanoseconds. And we have the wavelength lambda is equal to 193 nanometers. We have the diameter is equal to 1 milliliter. So the question is, it asks for what is P equal to? So how to find P? Yes, indeed. P is equal to E over T. So it's going to equal to 1 to the power of -3 over 15 nano. I do believe it's -6. So it's going to be 1 to the power of -3, 15 to the power of -6. So that would be 66.7 watts, and that's quite high. Okay. So during the brief time of the pulse, what is the intensity of the light? So then it asks for the intensity. What is the intensity equal to? P over A, someone said. Yes, indeed. So we have P over A. So that will be equal to P, and our A, since it is a circle, so it's going to be pi d over 2 all squared. So it's going to be 6.7 over pi of 1/10 power of -3 over 2 all squared, and that will equal to Am I doing something wrong here? What did other people get? That's insanely high. Okay. I have no clue about LASIK, so maybe it should be that high, or maybe it should not be. I really don't know. But to me, the steps so we've done looks fine so far. That is insanely high. One, two, three, four, 5, 6, 7. It makes sense why it is high, because it's such a small area. But yeah, is it? What does it give us the wavelength though? Give us the wavelength. I don't know. What does it give? Why does it give us the wavelength? Okay, so during the brief time of pulse, what is the intensity of the light wave? Yeah, and that's it. Doesn't ask for more. Huh. Well, I don't know. So yeah, maybe it needed to be that high to burn off something to shave off the tissue. Maybe. Okay. I know I'm much over time, but I want to do one more question. I do something about Doppler effect. So choose one of these. Let's take 43 because bio. really hope it doesn't have any displacement equation in it. Okay, a bat locates insects by emitting ultrasonic. And then lessons for the echoes from the bugs. Suppose a bat chirp has a frequency of 25 kilohertz. So let's try what we have. So given our frequency is 25 kilohertz, how fast would the bat have to fly and in what direction for you to just barely be able to hear the chirp at 20 kilohertz? Okay. Huh. So it asks for what frequency, like the frequency I hear. Okay, so this is F naught. Want to be. Oh, I see. Yeah. So when it's 25 kilohertz, you can't hear that. Yeah, but at 20 kilohertz, we can hear that. Okay, I see. So then the question is, yeah, how fast and which direction it's going. So now it's the case where you are stationary, but the source is moving either towards you or away from you. So my question to you is the bat moving towards us or like towards you or away from you for the frequency to decrease? Away, yes indeed. Okay, so then we do look at, yeah, so now we look at those equations and if the source is moving. So the frequency that you hear will be less. So we're gonna use this equation. So steps, let's call this F minus. So F minus is equal to the F initial divided by 1 plus Vs over V. Okay, so we need to find, it asks for, oh, whoopsie. No, I'm sorry, this is B, F negative is 20 kilohertz. And we do know that the V is equal to, let's say it's one of the speed of sound in air, which is equal to 343 meters per second, and it asks for Vs. Ask for Vs. So let us rearrange this and see what we get. So that will mean we will have 1 plus Vs over V is equal to F naught over F minus. That would also mean we would have Vs over V is equal to F naught over F minus minus 1. And finally, our Vs is equal to all of that, F naught minus F minus minus 1 multiplied by V. So that will equal to have 25 over 20. So that will be 5 over 4 minus 1 multiplied by 343. So 5 over 4 minus 1, apply that. Oh my goodness, yeah, that's 1 over 4. 343. Yeah, that will equal to 343. 85.75 meters per second. Meters per second. Away. Okay, so that's the final answer, and that's it. But just before we go, this is something I just want to try. Let's say, what if you use the other equation? Let's see what is going to happen. Okay, so let's say you used F plus. I actually don't know if there's anything, like any conclusion we make. I'm just curious a little bit what would happen. So we have the equation of that as F minus Vs over V. Okay, So that would mean that 1 minus v of s for v is equal to f over f plus. That means the v of s over v is equal to 1 minus f naught over f plus. And finally, vs is equal to 1 minus f naught of f plus. Yes, yeah, that's what that is what I was hoping for. So we'd have 1 minus 5 over 4 multiplied by v, which is equal to negative a quarter of 343, which is equal to negative 85.75 meters per second. So as you can see, like even if like you use the wrong equation, you will have the speed, but in the opposite way. So the equation still works. It's like if you don't know, oh, should it be towards me or away from me? Use one of them, like use the positive, because that means it's coming towards you. And if you have your answer in negative, that means it's actually going away from you. And the other way around. Yes, yes, only if you're moving towards a stationary sound. Yes. So, oh, so this one, yes, we only use it if I am moving or you are moving or whatever. The receiver is moving towards the source or away from the source. Yeah, yes, indeed. That's what it is. Okay, so does anyone have any questions? Stop recording.